All right, so we're going to move on to the next section here. With section 10.4, we're going to talk about a new type of angle called an inscribed angle. This is different than when we talked about central angles in the first half of the chapter. And so we're going to kind of talk about what it is, what are the different properties, and then how do we use them within the problems we're going to see. So the first thing, an inscribed angle. So any angle whose vertex is on the actual circle. So the vertex, the corner, has to be on the actual circle. So if we look at the picture below here, angle ABC, we see that the vertex B is actually on the physical circle itself. Okay? Now that's different than what we had before, where we had a central angle, like say angle DEF. So notice in this case, the central angle has that vertex in the center. Now, as far as inscribed angles are concerned, the really key thing here is that the angle measure is always half the size of the arc. So that angle is always going to be smaller than the arc. It's always going to be half the size. So angle B and angle arc AC. So I'm going to highlight the arc AC in red here. So this arc is twice as big as the angle that makes it. And so if I told you that this arc was 100 degrees, then we know that the angle inside would have to be half of that, or 50. Or we might work the other way. They might give us the angle measure and say like this angle is 30 degrees, and they want the arc measure, and so that would be twice as big, or 60. And so that's a really big thing, is on those inscribed angles, the angle itself is always half the size of the arc. So the outside's always bigger than the inside. And again, that's quite a bit different than our central angles, because in our central angles, if I use green here, if this angle in the middle was 50 degrees, then the arc is also 50 degrees. So for those central angles, they're identical. For the inscribed angles, when we go all the way across the circle, those angles are always half as big as the arc. Okay. The next thing with inscribed angles is the fact that if we have two or more angles opening to the same arc. So inscribed angles can happen anywhere in the picture because the vertices can be anywhere. They can be anywhere along the outer edge. And so what we notice here is we had an angle, ABC. Now angle ABC hits arc AC, so this arc right here. But then we notice in red that we have angle ADC, and now that also intercepts the same arc. It opens up to A and C. Now, if those are both part of the same arc, so let's say arc AC was 70 degrees, then that means each of those angles would be half that size. So if I wanted angle D, I would cut 70 in half and get 35. I would cut the 70 degrees in half and get angle B, which would also be 35. And so what we're seeing here, this congruent inscribed angles, if they intercept the same arc. So if I have two angles that open up to the exact same spots, then those two angles are going to be identical to each other. So in this picture, angle D would be congruent to angle B. And so that's always something we want to keep an eye out on. If I have more than one angle opening up to the same arc, they're always going to be identical. When we look at semicircles, so we go back to that second section in chapter 10 where we talked about arc measures, and we talked about semicircles. So if I have a diameter, so AC is my diameter, that means that my arc that goes with that chord, that diameter, so this case arc AC, would have to be 180 total degrees because I'm doing half of the circle. Well, so what happens here is if I create a inscribed angle, like ABC here, we just talked about that angle has to be half the size of its arc. And so if my arc is 180 total degrees, my angle has to be 90. And that doesn't matter where that angle is. So if I go from A over to D and up to C here, so we're going to call this point D, I'm still intercepting that whole semicircle, that half a circle, which means this is also going to be a right angle. And I can even go the other direction. So I could have an angle up here, go from A to, let's call it E to C. And since I open up to a semicircle, 180 degrees, that means my angle is going to be a right angle. So anytime you see my angle opening up to the endpoints of a diameter, so it's opening up to a semicircle, you know that that angle is always going to have to be a right angle automatically. Inscribed quadrilaterals. So if I have a quadrilateral four-sided object and each corner, so in this case H, I, J, and K, each corner is on the actual circle itself, then that's what's called an inscribed quadrilateral. And what's important to note here is that any opposite angles, so the opposite angles in those inscribed quadrilaterals are always supplementary or add to 180. So if I'm looking at an inscribed quadrilateral, opposite angles, the ones directly across from each other, always have to add up to 180. So if I take x plus 78 here, I'm going to get 180 degrees, which means x would have to be 102 degrees to make that work. And that works for any opposite angles. So if I were to tell you that I was 3x plus 10 and k was 2x plus 30, and I said find the value of x or find the measure of the angle, then you would simply take those two angles and add them together. 3x plus 10 plus 2x plus 30 would have to equal 180, and then you solve. And so you find your value of x, you could plug it back in and find either angle measure. And so every time you have an inscribed quadrilateral, so all four corners are on the circle, the opposite angles have to add to 180. As far as some examples then, kind of putting all of this together. So if we look at this first example, we notice that we have an inscribed angle. So my vertex Q is on the actual circle. And so that means that this angle is half as big as this arc. So I have two different options for solving this problem. I can either double my angle. So I can take two 2x plus 1s and set it equal to 96. The angle times 2 is always equal to the arc. And so I'd get 4x plus 2 is equal to 96. I then go ahead and take 96 minus 2. And so we get 4x is equal to 94. And then if I divide both sides by 4, I get 23.5. So there would be my x value. Now the other thing I could do with this same exact type of problem is if the angle is half the size of the arc, then I can cut my arc in half. So I can take 96 divided by 2, and I can say, well, 2x plus 1 has to equal 48. And then when I go to solve, I get 2x is equal to 47. I still get 23.5. So when you're working with these types of questions, you can do it either way. Now, for me, typically I will double the angle. That way I don't have to worry about any fractions depending on where the x's are. And so that's kind of an up to you type of thing. It's not equal to. So it's not 2x plus 1 equals 96. I have to double the angle or cut the arc in half in order to set those two things equal. Another example here says find the value of x. And so if we look at this picture here, we notice that the only two things that have x are these two angles right here. Well, so notice where this x is. If I open up that angle, it opens up to points M and A, so I get this arc right here. And then if I look at my other angle, which is angle T here, then for angle T, I notice that it opens up to arc MA. And so since both of them open up to the same arc, that means those two angles have to be congruent to each other. So I can take the 2x minus 3, set it equal to x, and then I can solve. We would get x equals 3. So anytime we see two angles open up to the exact same arc, we know that we're going to have equal angles. And so in this case too, besides angle H, so angle H in this case was congruent to angle T, we also would know that angle M would be congruent to angle A because those open up to the same arc down here. And so there's lots going on here that we could utilize in terms of these angles are the same, these arcs are the same, and so on. Now in the last example here, we're going to find a bunch of different arc measures or angle measures depending on what they're asking for here. And so we're just going to kind of take it one step at a time. So as we kind of go through this, the first thing it wants to know is the measure of angle U. So here's angle U right here. Now if I want angle measure, I need to know what arc goes with it. So if I open up angle U, so I follow it out to H and follow it out to E, notice how that opens up to a diameter. So EH is a diameter here, which means this whole angle in green, so this whole angle in green is 180 total degrees, which means my angle measure would have to be half of that, and this is one of those where I get my right angle. And so the measure of angle U would be 90 degrees because it intercepted, it opened up to a semicircle. As we're looking at this then, the next thing it wants to know, so we'll go to pink again. I want the measure of arc CH. And so if I highlight arc CH, and this is going to help you guys if you kind of highlight the pieces you need as you go. So arc CH, if I follow it back to where it starts, so I can follow C back to E, and I can follow H back to E, we notice that we have this angle 36, which means the arc measure would have to be twice as big as that. So if I double the 36, I get 72 degrees. There's my arc measure. And then as we continue to work through the problem here, if we go to arc CE, so highlight arc CE. Now this one, if I follow it back, doesn't have an angle that goes with it. It has H, which I don't have a measurement for. So I have to think about this a little bit differently. Notice on this top half of the circle, the whole arc, so this whole arc from H around to E, we already said was 180 degrees. Well, so if this side is 72, that means if I subtract from 180, the other side would have to be 108 degrees, and there's my measure of arc CE. Then, if we move to the next piece, it says the measure of angle CHE. So if I trace the letters C to H to E, so if I trace those letters C to H to E here, that means I open up to this arc that I'm highlighting in purple now, which we just said was 108 degrees. Well, so that means my angle measure would have to be half that size, which would be 54 degrees, and so there's my angle measure. And then the last one asks us to find the measure of arc ET. Well, so if I highlight arc ET here, so here's my arc. If I trace it back to its starting point, it goes back to point C. And so we see that that angle is 25 degrees, which means when I bring it outside, I have to double it. And so arc ET would have a measure of 50 degrees. And so when you're working with these more complicated pictures, just take it one step at a time. Match the angle to the arc and work it out. It's either double to get to the outside or cut it in half to get to the inside, and then just take it piece by piece as you go. With that, you should be able to start the worksheet that you get in class today or get off of Google Classroom. As you're working through that, make sure that you ask questions and make sure you access the answer key as it becomes available to help you with any questions you might have.